Hello students. So far we started looking at how to make the pipelined execution of instruction as close to the reality as possible. Right, in the process we started addressing quite a few assumptions that we made. A quick recap of them. The very first one was we introduced the interstage buffers or the pipeline buffers to store the unfinished instructions. Following that, we had a discussion whether uh, all the tasks that we split the entire process of execution into, whether uh, they'll be equal or not, and if they are not equal, what is the possible way out, right? And following that, we started uh, looking at some of the events which are called hazards, which obstruct the smooth flow of the pipeline. The very first one we saw was structural hazard, and we introduced a faster register file wherein we write to the register file in the first half and read from it in the second half. And to avoid dependency on the memory during the fetch and memory stages, we separated them out. We now have two memories, instruction memory and data memory, right? And we also understood that we need a lot of extra hardware that will supervise or the control circuitry, which will ensure the smooth flow of instructions, need to be uh, much more complicated when compared to a simple non-pipeline version, right? And we also looked at the possible scenarios where the execution of one instruction is dependent on another. We have data hazards in that, and we looked at stalling and data forwarding as part of hardware solutions, and inserting no ops or if possible reorder the instructions as the software solution. And over the past couple of classes we started looking at control hazards, and specifically at the hardware. We looked at how we can bring in some logic from execute to decode, etc. And moving on, we started looking at some more complex solutions which are primarily based on prediction of branches. In specifically in the previous class, we looked at the static branch prediction. Now we are going to look at the dynamic branch prediction. Okay, let's dive deeper. Dynamic branch prediction, as the name says, we are going to make a prediction based on the dynamic behavior of branch. Now, what do we mean by dynamic behavior of branch is when the program is executing, it means that when the particular branch is getting executed, right? Can we use the particular branch's behavior, how it behaved in the previous instances, and make some guess on what would happen at this instance, right? So that is called the actual branch behavior. So basically we look at the history of the branch and history of outcomes of the actual outcomes of the branch and make a guess on what would happen this time. And the moment we say we want to look at the history, it means that we need some additional storage. What specifically it means is we are going to store for each branch in the previous n number of instances whether it was taken or not taken, and we are going to use that in the n plus 1th instance and make a prediction, right, whether this time it will be taken or not taken. We'll start from the simplest one, which is the 1-bit prediction. It's also called last time predictor. What in a single statement it would mean is we will look at what happened when we executed this branch the previous instance, right? And if it was taken this time too, we are going to predict that it will be taken. Now if in the previous instance it was not taken, then this time we would predict as not taken. This is the simplest explanation for 1-bit branch prediction. So it would consider just the last instance of the branch and look at its actual direction, whether it is taken or not taken, to make the prediction. And the working of the one bit branch predictor is quite easy to explain and understand if we look at it as a state diagram, right? And its states are represented as PT, which means likely to be taken, and its prediction would be taken. When the predictor is in PT stage, state, it would predict as taken, and PNT is likely not to be taken, and the prediction is not taken. And a quick note here, the states are actually the predictions, and the transitions among the states happen based on the actual branch outcomes. Let's look at the one branch predictors diagram now. We have two states, predict likely not taken, predict likely taken, and let's say that predict likely not taken to be our initial state, right? As long as the actual outcome of this branch is not taken, we will continue to predict that it will not be taken this time also. Now, if we see that in the previous instance, we predicted not taken, but the actual outcome is taken, right? Then we would move to the next state, which is the predict likely to be taken. Now we will continue to be in this state as long as the actual branch outcome is taken and our prediction is taken, right? Now, if the actual branch outcome when we are in predict likely taken is not taken, then we will switch back to PNT, right? Now, the key thing to observe is the switch among the states will happen whenever there is a misprediction, right? When we were in predict not taken and the actual branch outcome was taken, then we will switch to predict taken, and we'll continue to be there as long as the actual branch outcome is taken. But if we see that the actual branch outcome is not taken, again it is treated as mispredict, and we are going to transition to PNT. Okay, now let's try to understand its working a little more closely by looking at a few examples, right? So let's assume that we have a one bit predictor and its starting state is predict not taken, and now we want to calculate how accurate it would be for a sequence of branch for a sequence of instances of the same branch actually, whose outcomes are like this: taken, not taken, taken, not taken, 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 not taken, not taken, and taken. Okay, so T represents taken and T represents not taken. So for convenience, I put a small table here that will explain us, that will help us understand how the one bit predictor would predict and what would its accuracy be. So we have few entries. CS stands for the current state of the predictor. Pred is the actual prediction that the predictor would make. AO is the actual outcome. H/M is the hit or miss, whether this prediction was hit or missed by this predictor, right? And NS is the next state. Now let's start with the predict not taken. We would predict not taken in this state, but the actual outcome, if we observe, is taken. So when we compare the prediction and the actual outcome, there is a mismatch, which is called as a misprediction, right? Whenever there is a miss, the predictor will change its state. The next state now would be predict taken, right? So we will start in predict taken. In this state, as the name says, we would always predict taken, but the actual branch outcome is now not taken. Again, there is a mismatch, so we will make a transition to the other state, which is PNT. So for the third time, we are going to start with PNT. We are going to predict not taken, but the actual branch outcome is found to be taken, right? And again, there is a mismatch, so we transition to predict taken. So for the fourth instance of the same branch, the branch predictor is in PT state and it would predict taken. But if you look at the actual branch outcome, it is not taken. That is leading to another misprediction, right? And because of this misprediction, we are going to transit to PNT. For the fifth time, the predictor is in PNT state. It would predict not taken, but the actual branch outcome is found to be taken. So again, it's a misprediction and we will transit to PT. The sixth time, we start in the predict taken state. We will predict or the 1-bit branch predictor would predict that it would be taken, and if we find the actual branch outcome, it is indeed taken. So it is a match. It is a hit prediction. Because it's a hit prediction, we will continue to be in the same state. Here it's PT, right? So in the next time, we are in the PT state and we predict taken, but the actual branch outcome is not taken. So it's a misprediction again. So we will transition the state. We'll go to PNT. So the next time we start with NT, we'll predict. We'll start with PNT. We predict that it will not be taken, and we find that the actual branch outcome is also not taken. So it is a hit prediction. So we will continue to be in predict not taken state. So for the last time here, we are in predict not taken state. We will predict not taken, but the actual branch outcome is taken. Again, we see a mismatch, and so we will switch the state to predict taken. The next time when we want to use the same predictor for this branch, it will start with predict taken. Okay. Now, if you look at the total number of times we use this predictor, it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have consulted this predictor 9 times, and of those 9 times, only 2 times it has provided a hit prediction. So the accuracy of this 1-bit predictor is 2/9. Now let's do the same exercise, but here we are starting with predict taken state. Okay, so here we have our table with the entries current state, prediction, actual outcome, hit or miss, and the next state. So the current state, the initial state is predict taken. So we'll predict taken, and the very first time we are looking up at the actual branch outcome, it is taken. So it is a hit, and so we continue to be in predict taken state. The second time when we look up, it will predict taken, but the actual branch outcome is not taken. So we see a mismatch. So we shift the state to PNT. The third time we start with PNT, it will predict not taken, but the actual branch outcome is taken. So again we have a miss. So we will go to predict taken state. The fourth time we predict taken, but the actual branch outcome is not taken. So it is a misprediction. So we'll transit to PNT. The fifth time we'll predict not taken, but the actual outcome is taken. Again, it's a misprediction, and we will switch to PT. The sixth time we'll predict taken, and we find that the actual branch outcome is also taken. So it is a hit prediction. We will not change our state. We continue to be in PT. The seventh time we start in predict taken state, and the actual branch outcome is not taken. So there is a mismatch. So we switch the state to PNT. Eighth time we start with PNT. We'll predict that it will not be taken, and the actual branch outcome is also not taken. So it is a hit prediction. So we continue to be in PNT. The last time we start with PNT, we'll predict that it's not taken, but the actual branch is taken. Sorry, the branch actual outcome is taken. So there is a mismatch. So we switched it to predict taken. Now, if we look at the accuracy of the same 1-bit branch predictor, which is starting with predict likely to be taken as the initial state, it is 3/9, because we provided 3 hit predictions when consulted 9 times. So let's look at a few other examples to see how good the one bit branch predictor is. Now, if the actual branch outcomes are like this, so we have a sequence of taken, 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 and a sequence of not taken, etc. Right? So if we look at these and let's see how much the accuracy would be. If we are starting with predict taken state, for the first 10 predictions, we'll predict taken and the actual branch outcome is also taken. So they are all hit predictions. Now the 11th time we will predict taken, but the actual branch outcome is not taken. So it is a misprediction. Accordingly, we will switch the state to predict not taken. And the remaining 9 times from 12 to 20 here, all the branch outcomes are not taken and we will continue to be in predict not taken state, and all of them are hit predictions. So here the accuracy is the first 10 times are hits, 11th time is a miss, and the remaining 9 times is a hit. So it is 19 upon 20. For the same branch outcome pattern, if you look at the one bit predictor which is starting at PNT state, right, it looks slightly different. The very first prediction itself will be a mismatch, because in PNT state we will say that the branch will not be taken, but the actual branch outcome is taken. So this will count as a misprediction and we'll switch state to predict taken. The next 9 times we are going to make a prediction that it will be taken, and indeed the branch was taken. So all the 9 will be hits. The 11th time we are in predict taken state, but the actual outcome is not taken. So it is a misprediction and we switch to predict not taken state, and the remaining 9 times we will have hit predictions because we are predicting not taken and the branch is also not taken. So here the prediction accuracy is first time is a miss, next 9 times it a hit, then 11th time is a miss, and last 9 times is a hit. So it is 18 upon 20. Let's look at one more example. Just we have flipped the pattern. The first 10 times the branch will not be taken, the next 10 times it will be taken. So a key point to understand is the branch was executed 20 times and these are the outcomes each for each instance of execution. Okay. So if we start with the one bit branch predictor in PT state, so it looks similar to the second half of the previous slide. The very first time we are going to make a misprediction, we are going to switch to predict not taken. The remaining 9 times we are going to predict not taken, which will be a hit, and the 11th time we will predict not taken, but the actual branch outcome was taken. So it is a misprediction. Accordingly, we will switch the state to predict taken. That will continue for the remaining 9 instances. So the accuracy would be first miss, 9 hits, and 11th one is a miss, and remaining 9 are hits. So it is 18 upon 20. If we start with PNT, now it's more or less straightforward. For the first 10 times they are hit predictions. The 11th time will be a miss prediction and we'll switch the state to PT, and the remaining 9 times will be hit. So the prediction accuracy is 19 upon 20. Right. So the key point here that I want to convey is the starting state of your branch predictor has a say on the accuracy. But if the branch is executed, let's say 100 or 1000 times, then the very first state where you started will not matter. More or of course there will be slight change in accuracy, but that's not too big to notice anything, right? So let's take another interesting example where the branch is switching between not taken and taken. So here we have 20 instances where the branch starts with not taken. Then the second time we execute the branch, it is taken. Third time it is not taken. Fourth time it is taken, so on and so forth. So if we start with the predict taken state, right, the very first time we predict taken, but it is not taken, so we switch to PNT. The second time we will predict not taken, but the actual branch outcome is taken. So we'll switch back to PT. The third time we'll predict taken, but the actual branch outcome is not taken. So we'll switch back to PNT again. So this will continue. So all the predictions that we are going to make are mispredictions. So the accuracy here would be 0 upon 20. If we are starting with predict likely to be taken state. Now what happens if we start with the other state, predict likely not to be taken? The very first time it will be a hit. The second time we will predict not taken, but it is the actual outcome is taken. So we switch states to predict taken. The third time what happens is we are in predict taken state, but the actual outcome is not taken, right? So it will be a mess. We'll switch to predict not taken state, but the fourth time we'll predict not taken, but the actual outcome is taken. So on and so forth, it will continue, and only for the first time we'll make a hit prediction. For the remaining 19 times we are going to make a misprediction. So the prediction accuracy is 1 upon 20, quite low, right? Now the interesting aspect is if you look at the static branch predictors, right? Let's say we are looking at always taken static branch predictor. It will always predict taken. It doesn't store any history or anything like that, right? But if we are always predicting taken, for this pattern of 20 instances of the same branch, even if we predict always taken, right, it will be a hit prediction for 10 times. So the accuracy of always taken is 10 upon 20. Also, if we say that my static branch predictor will predict not taken all the time, even in that case we have accuracy of 10 upon 20. So this is one specific case where the dynamic branch predictor, specifically the 1-bit branch predictor, is beaten by a simple static branch predictor, right? So the reason being the branch outcome is flipping every time. So whenever we have such branches, the 1-bit branch predictor is not a good branch predictor. So in general, the 1-bit branch predictor will quite well work for the loops, because the very first time we are executing that branch, right, that's when we are going to make a note that it is taken the first time. From second time till the nth time, we are going to make a predict that it will be taken, etc. But the nth time, if we imagine the loop is for n iterations, for the nth iteration, the branch will not be taken, but our predictor will still predict taken. So only the first and the last iterations of the loop will be mispredicted. So accuracy in general would be n minus 2 upon n. Now if n is large, so we will have high accuracy. But if the n is small, means the iterations of the loop are quite low. Let's say we are just iterating for 5 times, for example, and the first and last are anyways mispredict, so the accuracy drops to 3 by 5. Excuse me. And if the branch is behaving as taken, not taken and all, the accuracy is even low. This is what the discussion is on the 1-bit branch predictor. We are going to extend it further for 2-bit and n-bit branch predictor, and further we are going to extend it considering the histories of multiple branches together. So here for this entire discussion we were considering the history of only one branch, right? But typically our program has multiple branches. Now do we have any link between how one branch executes and does it have impact on another branch which is following it, etc., which is typically called branch correlation? To exploit correlation, we come up with something called global branch predictor. That's what we are going to discuss in the next couple of classes. With that, I'll pause now. Thank you.